Let's go ahead and start up lecture. Okay, so last time I left off on a cliffhanger, and so I hinted that the way you were told to round when you got to 5 was wrong. And that's because when you get to 5, right, you have 0 through to 10. Okay? And the middle point of all of that is what? 5 is 5 is smack dab in the middle of that. And so what you're seeing there is that if you round 5 up every time, you're actually going to end up with a larger and larger number the more times you do that, right? If you round it down every time, you would end up with a smaller and smaller number every time. Do you guys know what your bank does? It rounds everything down all the time. Yeah. So they go like 2 decimal places out, round it down, usually, and then they just keep that money. Anybody know what famous movie has that in it? Superman 2. Yeah, and also a Ukrainian group did that like 10 years ago and stole, I believe it was $300 million. They did it over like 3 days. So. That group disappeared. Nobody ever heard of them again. So it's estimated that they may have been murdered in Russia, actually. But anyways, weird history around it. Now, what you would do if you want to do this accurately. Now, in your exams, it's not really going to matter because you have, multiple choice. So for the most part, this is never going to come up. But what you would want to do if you ever do this for a business or if you ever do this on a spreadsheet because you're working for a company, is you would want to round up half the time and round down half the time. And to facilitate that, there's a set of rules. And so if you end in an odd number, you typically round that up. If you end in an even number, you round that down. Okay? And so, for example, this one would be 0. I'm sorry. Let me put this even number. Okay. So this right here would be like if you're rounding this 0.5, you're going to round that to I need one. Get there. Otherwise, I would have rounded 0, right? And that would. All right. You would round down for that one. So this would be right here. You would round up for this one, like so. Okay. So this one rounds down. This one would round down. And you do that over and over and over, and that should give you essentially an even split of rounding up and down. And so you'll be off on everything, but they'll cancel out, right? Because you'll be off different directions on everything instead of stacking that error. Let's kind of think about that in terms of the Superman computer virus, right? Or the Ukrainian group's computer virus, or actually somebody did in the 1980s as well and stole a bunch of money from the banks. So the Ukrainian group, they actually infected a bunch of ATMs at this very large branch of banks in California. And so what they did is they just wrote code that every time that the bank calculates interest, does any sort of calculation, okay? Whenever they do that, it would be something like you would get maybe $3.91523, whatever, right? When they do the calculations. Most calculations don't end nicely with the digits, right? And so what would happen is the bank actually tries to round these in semi-reasonable ways. It overall rounds down for you, but they don't get super aggressive. Okay. What these people did is essentially the bank rounds here. They took this. Okay. So they took it a couple decimals down from where the bank rounds. And what they did is they took that 0.00003 cents. That's USD dollars. And they took that and they put it into an account that was in their name. Okay. It was overseas account, so you can't get it back. But now, that's not a lot of money, is it? Except, how many times does a bank do calculations in it? Millions and millions and millions and millions of times, right? Big banks could do millions of calculations in an hour. And so you could be stealing every second $3, right? Anybody know what sort of money you're looking at? $3 every second? In an hour, you'd be looking at like $10,000, right? Yeah. So you can steal very large amounts of money by doing this. Within 3 days, they stole a little over 300 million. It was closer to 400 million, actually. Yeah. And nobody can realize it. Also, a great movie, Office Space. If you watch that movie, it's a comedy. That actually is part of the plot. They do the same sort of virus, but they screw up the digit. And it steals all the money in like one day. So whoops. So that's one of the reasons why like significant figures, rounding is so important, right? This is a financial use of this. Okay. Science also has its own use, obviously. Obviously, there is financial sciences too. So now, when we do these significant figures, once we figure out significant figures, adding and subtracting and multiplying and dividing are going to change those significant figures. Okay, so let me think about it this way, okay? So you know your account down to the penny, all right? Somebody adds approximately $1,000 to your account. Are you going to know the penny down to the penny anymore? They don't know if they added 1,300. They don't know if they added 1,200. You know, it's around 1,000-ish. Okay, it could be 900. But that penny amount just does not matter to you anymore, does it? Okay, and it just is not a something that's going to help. You know, your uncertainty is up in the hundreds, isn't it? Hundreds of dollars. Like if you were off on your calculation and you spent $1,026, and then you're like, I'll have 20 cents left. Well, if they added $900, you're screwed, aren't you? You're going to go over and get all the fees, aren't you? So that extra little bit of certainty that you had, when you add and subtract from it, that's going to change depending on the decimal place, okay, of what was added and subtracted. Now, let's think about multiplication on the other hand. So let's do the other way example real quick. What if I charged you 0.1 cent? Is that going to affect your mental calculations of how much you have in your bank account? No, you don't care, right? People do that all the time to you. You don't care. And so what's going to end up happening is that's not going to affect anything, right? Your sig figs are still the same. Your uncertainty is still the same, right? Now, what if instead that would have been 0. That would have been that number, right? In terms of dollars, okay? What if I said, I'm going to multiply your account by that? So you have, let's say you just got all your student loans and stuff. You have $20,000, right? I'm going to multiply your account by that. Are you going to be happy with me? No, you're going to be damn near bankrupt, right? It's all gone, okay? You invested it in some crypto coin. That's what's remaining, right? You got 1% next day. Actually, that is pretty. That sounds like an actual crypto coin investment. 1% remaining. There you go. So that percentage really, really matters when you're talking about multiplication division, doesn't it? Okay? Multiplying something by a very small number or very large numbers has a huge effect. Okay? On the other hand, subtracting and adding very, very small numbers to larger numbers, no effect at all, right? And so the rules for uncertainty are going to change depending on this. What you're going to do for addition and subtraction is that you're going to take your answer, and the number with the least number of decimal places is the one that's going to be where you cut that off. Okay? And so if your least number of decimal places is no decimal places, you're going to cut that off at no decimal places, right? If you happen to be the hundreds that you know this to, that you have some degree of certainty to, well, you're going to cut off there, right? Because I'm not going to know if I have $1 or not. If somebody transferred in something they're not sure what it is to hundreds, right? Is that making some sense? Okay. Now, the multiplication, that one you have to count your number of significant digits, and your least number of significant digits is going to change how many sig figs significant digits you have. Okay? So how many significant figures you have is going to change on the least number of sig figs for multiplication and division. On addition and subtraction, you don't have to worry about sig figs till the end. What you worry about is the least amount of decimal places. Okay, so your book actually states something that's slightly incorrect for 5, that you would round that up all the time. That is fine to use in the tests and stuff. It's not going to change things. It is incorrect. Okay, mathematically it is incorrect. You do not always want to round up. Now, the large number with no decimal point, you need to substitute zeros for numbers that are not significant. When we do multiple step calculations, what you should do anytime you do multiple step calculations is you should always give yourself an extra 2 significant figures while you're doing the calculation, and then change the number of sig figs at the end. Okay? If you change and like round up, round down every single time you do a calculation step, you're going to find your answers are coming out like a few decimal places off of the correct answer all the time. And you're always wrong by a little bit. Okay? And so it can actually build up and matter quite a bit if you do this enough times, right? So if you did this in your spreadsheet enough times, you would end up with a significantly different answer. Okay? Now, scientific notation, this is what this looks like. This would be a coefficient. It's going to be something with a between 1 and less than 10. Okay? You don't typically put a 0.1 for the coefficient, and you also don't put an 11, right? Because what you're going to do is you're going to multiply that coefficient by 10 to some power. Okay? Let's say I want to express 100. How would I express 100? Well, that'd be 1, right? And then times 10, and then how many zeros are in 100? 2. And so you'd do 10 to the second. Okay? 1,000 would be 10 to the third. Right. Now, this is a very, very convenient way to represent numbers for scientists. One of the things you're going to notice is that this avoids that awkward situations we were talking about with sig figs, where you have those placeholder zeros that you can't get rid of. Right? You don't have placeholder zeros here because you can represent any number by doing 10 to the power of, right? And so 10 to the positive powers, those are going to be large numbers like hundreds, thousands, right? 10 to the negative powers, those are going to be your small numbers like 10 to the negative 1 is 0.1, right? And so we can avoid that entire situation. Your coefficient has the number of significant figures it should have. That's it. You don't have to worry about anything else. Okay? Makes life a little bit easier. This right here is the pattern that you should see on this. And so what you'll see is like 1,000,000 is 1 times 10 to the 6th, right? 2,000,000 would be 2 times 10 to the 6th, right? And then down here, we have the small numbers. And so, for example, this would be like the micrometers that we were talking about. So 1 over 1,000,000, that would be, well, 1 times 10 to the negative 6, right? Okay. If this was 5 here, this would be 5 times 10 to the negative 6, right? There you go. Now, a little side note that 1 times 10 to the 0, the power of 0, always takes that down to 1. And so that would be 1. Okay. You wouldn't have any difference here. So nobody ever writes that 10 to the power of 0 for scientific notation. Okay. But technically, yes, it could be there. Okay. You can always take anything times 1, right? Okay. Let's talk about percent. So percents are better stated as parts per 100. Okay. And so what they are is you're going to have the amount of parts divided by the whole, right, times 100 to get a percent. Now, you will oftentimes see people say times 100% because the percent is treated as a unit oftentimes. Okay? And so keep in mind if you see that, it is times 100 and now you are percents. Okay? It is not put it in your calculator part, so 1 out of 30 students, and then times 100, then I hit percent. That would give you a very different answer. If you go on your calculator, that percent button is doing this last one. Okay? It's times 100. So if you did that, it'll give you times 10,000. Okay? Very different number. All right. Now, again, these fractions, these can be converted to percentages by dividing the numerator by the denominator and multiplying by 100 when we put a percent sign, right? A decimal number can be very easily converted to percents. You probably have all done this before by just moving that decimal place 2 over, right? And so that would give you the percent. If I gave you a 0.12, what would that be in percents? Times 100, right? So multiply by 100, that would give me 12%. Okay. Okay. Now, let's talk about the stuff, the matter that everything's composed of. We've kind of talked about some of the divisions of matter, but how do we measure that matter? Okay. And let me add in, if I say I have 1 of something, do I have a lot or a little? Does it have meaning right now? Saying 1? No. What am I lacking? I'm lacking units, aren't I? Okay. Scientific number, and really any number, doesn't have a meaning until you have both the number and the units. Okay. So you have those two things together, it really doesn't have any meaning to it. I could have 1 planet, in which case, man, I'm doing great. I could have $1 million, right? In which case I'm doing pretty good. Or I could have 1 penny, in which case I'm not doing so great. Or 1 feather, right? It just doesn't have any meaning without the units. So mass, this can be anything that takes up space, and also be placed on a scale and weighed. This is going to be a measure, the amount of material in an object. This is a very standard definition. It's kind of a circular definition because it doesn't have any definition that backs it up. Mass can be thought of as sort of like resistance to you pushing something in space. Okay, so if you push against the planet, you don't move the planet a lot because it has a lot of mass, right? You move yourself a lot because you don't have very much mass compared to the planet. Okay. So the common unit that's going to be used to measure mass is going to be the gram. Now, people oftentimes equate grams and kilograms to pounds. They are related, but pounds is not actually a measurement of mass. Pounds is a measurement of weight. And so what weight is it is the gravity of the planet pulling on you. Okay? That makes sense? So if you were to measure something in grams and kilograms, it would actually measure the same kilograms and grams on any planet. Not with the same equipment. You'd have to calibrate and change the equipment, but it would still be the same grams and kilograms. Okay? Pounds, on the other hand, pounds force, that sort of stuff, that's a measure of force or weight. Okay? Now, the weight of an object is going to be determined by, again, the pull of the gravity on the object. it's going to be proportional to the mass, but it's going to be a force that changes depending on your location. So your weight actually does change as you move around the planet. If you go higher, you'll weigh slightly less. If you go lower, you'll weigh a little bit more. Okay? And so your weight actually varies, not enough for you to really care, but it does vary depending on where you're on the planet. And you've all probably seen the astronauts up in space, right? And they weigh near nothing. Okay? And that's why they're floating around, right? They still have the same mass, and they still have that same inertia. So they have to like push off against things, right? They can't push off against a feather and they're going to go anywhere, right? Because the feather has much less mass. Now, as long as an object is weighed in roughly the same location on Earth's surface, its mass and weight will have the same measured values. And so typically we use these interchangeably when we're in the lab because we're all going to be in one place, right? We're going to do all our measurements in one place. Won't matter much, okay? Now, volume. The volume is going to be the three-dimensional measure of the space occupied by the matter. You're probably all somewhat familiar with volume. In the lab, the volumes are going to be routinely measured using things like graduated cylinders, pipettes. You'll use those two things by far and away the most. You may use a burette, but what you won't use is something like a beaker, okay, or an Erlenmeyer flask. And that's because they have horrible uncertainty. Really, 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 really high. Okay? Let's say that you wanted me to make you pancakes, and I went, I'm just going to use this to measure my cups. Would you be very happy with me when you get your runny pancakes that will never actually solidify properly? No, that's going to stink, right? Not going to be good pancakes. Yuck. Why is that? Because this uncertainty for measuring one cup is ridiculously bad, right? I can't tell what one cup is in this. And even if I knew this was actually 4 cups in here, okay? That doesn't help. Like, I don't know exactly where the, 1/4 of this is, do I? Because it curves. So, like, it's just not what you measure with, right? Just like you would not measure with tables when you're trying to measure something, right? Now, the unit typically used in the lab is going to be called the milliliter. It's going to be 1,000th of a liter. In clinical settings, the volumes will often be with calibrated syringes. And so this would be a calibrated syringe right here. We also use that in some of the labs, but the ones that can measure out well and are not plastic are quite expensive. So, whenever you see a syringe, typically this is going to be cc or centimeters cubed. That is actually the exact same amount of volume as a milliliter. 1 milliliter will actually be a cubic centimeter, and this will be 5 milliliters is actually a teaspoon. By the way, you can use that to help you out if you ever need to measure out coffee or something. I've converted all my coffee measurements into milliliters because I keep buying these European coffees. I need to figure it out. So density. Density is the small d. This is actually a comparison unit. What you've done is you've made a ratio between the mass to its volume. Okay, and that's what density is. And so density equals mass over volume. It is done in units, typically, of grams over milliliters. And so it would be a number in grams over a number in milliliters. And the unit of density is grams per milliliter. The density of water is going to be 1.00 grams. It does change a little bit depending on the temperature, but we've done a little trick here, and we've actually made this number. So if you use sig figs, that'll be consistent for basically all situations you'll be in. So 1.00 grams per milliliter, that's the density of water right there. That's water. And so if you put something that has a lower density than water, what happens? It floats. There you go. If you put something with a higher density than water, what happens? It sinks. It sinks. Now, this relationship with water, this is an incredibly important relationship, right? It tells you, is it going to float? Is it going to sink? sounds really important to like everything that happens in the world, right? So we have a special relationship just to denote this, okay? And it's called specific gravity. So the liquid density is going to be measured with respect to water. And the density of water is going to be 1 gram per milliliter. This is actually at 4 degrees Celsius, in case you're curious. It goes to like 0.9997 at like 0 degrees Celsius, and then it goes up if you get a little bit warmer. Okay, if you get hot enough, you'll actually see it goes up enough that it really matters. You'll actually, if you do it in a small bottle, it'll go up and flood. And so the ratio of the density of a sample to the density of water, this is referred to as specific gravity. This is the abbreviation, SPGR. And all that is you just take the density of the sample you're looking at and divide it by the density of the water. Okay. Now, note that at 4 degrees Celsius, it's just the same number. The only difference is it does not have units, because your units would actually cancel out the grams per milliliter. Okay. So it is actually a unitless number. Now, one of the things you should keep in mind is when you're changing the temperature, then you're going to be dividing by something that's not 1. Okay? So if you do this at like 100 degrees Celsius or 90 degrees Celsius, that sort of stuff, these will not be values that are just 1. Okay? You'll actually have a like 1.1, 1.05, that sort of thing. Okay, so the specific gravity of a liquid, this can be measured with a simple instrument. It's called a refractometer. This is a very, very common instrument to find in like labs for hospitals. Okay, because there's quite a few tests that are run on various different biological fluid samples. They're essentially just measuring their specific gravity. If they're too high, they're too low, then you know something's wrong. And then you can go on and do more expensive tests. Temperature. So we've talked a little bit about temperature, but we measure temperature of a substance to determine its hotness or coldness. This is the definition your book gives. It is, again, a circular definition. If you want to understand temperature, it's actually a measure of randomized kinetic energy. You guys know kinetic energy? It's the energy of something moving through space, right? At a specific speed and mass, right? So if you have one object doing that, not a problem. You can calculate kinetic energy. But what happens when you have 2, 3, a million, a billion, a trillion times a trillion objects doing that in all different directions, different speeds, different masses? It becomes almost impossible to figure out, right? You don't even want to think about it, do you? And so what we do is we measure that and we call that temperature. Okay? And so it's just randomized kinetic energy of a system. All right. Now, this is typically going to be done using a thermometer. There are also electronic temperature probes, of course. In the United States, we're going to use the Fahrenheit scale. Most of the rest of the world uses the Celsius scale. There's a few places that use the Fahrenheit off and on. I can't think of any countries other than the U.S. that exclusively uses it, though. Scientists actually use a completely different scale, especially in modern science, or if they're actually in the field that this depends on. And that would be the absolute scale, which is the Kelvin scale. Okay. You notice that these are all called Fahrenheit, degrees Celsius. That's the same thing as like a circle, right? You have like a circle, and you have the degree that you're different, right? That happens because you don't know where the beginning of a circle is. So all you're measuring is, I've chosen this point, and I'm this far off at that point. Okay? And that's what the Celsius and Fahrenheit scales are. Now, there is actually an absolute zero, as it turns out. We didn't learn that right away. It took a while to figure that out. But there is an absolute zero, where there is no randomized kinetic energy. Everything's just frozen in place, and there's no random kinetic energy. And so that's absolute zero. Okay? Technically, you can be moving and be absolute zero. Everything has to be moving in the same direction, though. It can't be randomized. So this is the temperature scales and how they relate to each other. So if we look at the Kelvin scale, that starts with 0 and it does not have a degrees. Okay, because there's an absolute scale, we know there's a 0. And so we would then measure up from that. The freezing point of water would be 273 Kelvin. Okay, 273.15 Kelvin actually, but 273 is usually good enough. That in Celsius is 0 degrees Celsius. Okay, I actually really like Celsius. If you ask me which one degrees Celsius, it still probably doesn't matter, but I think that it being 0 at freezing point of water actually is really nice. Because water's frozen outside, 0. There you go. Okay. And that in Fahrenheit is 32 degrees Fahrenheit. Y'all probably kind of knew that because your car goes ding and it's 34 and you look around, oh, it's 32 under the bridge, right? Yeah. When we're talking about the normal body temperature, Kelvin, that'd be 310 Kelvin, 37 degrees Celsius, and 98.6 Fahrenheit. Okay. And then over here we have boiling point of water. It's 100 degrees Celsius. That's the easiest one to remember. So 0 to 100 on Celsius, just freezing point, boiling point of water. Okay. Really nicely standardized. Kelvin is 373 Kelvin. And then Fahrenheit is 212 degrees Fahrenheit. You'll notice that Fahrenheit does not have the same number of separations between freezing and boiling as Celsius does. It is not 100 degrees separating those two. Fahrenheit has 180 degrees separating those two. Okay? Celsius has 100 degrees separating them. And then Kelvin is actually based on Celsius. So we had the Celsius units because we knew what freezing point of water was for a long time. And then we figured out, hey, there's an absolute 0. We can start this unit scale from 0. Cool. And made the Kelvin, right? So how big was 1 Kelvin going to be? 1 degree Celsius, right? Why bother remaking it? So if you want to convert, Kelvin equals degrees Celsius, that whatever that number is, 0, 100, whatever, plus 273. Okay, and that's going to give you your kelvins. If you want to go from kelvins to Celsius, what do? Subtract, right? You just subtract that 273 over. Okay? Okay, now, if you want to go from degrees Fahrenheit to degrees Celsius, what you do is you plug this in right here, okay? And so you'd put your number of degrees Fahrenheit right here, minus 32, and then you take that number and you divide it by 1.8. Okay? Now, funny enough, I actually remember this number right here as 100 over 180 because I know the separation between the scales. I don't remember the 1.8. So if you want to go from degrees Celsius to degrees Fahrenheit, what you're going to do is you're going to take that degrees Celsius number, you need to multiply it by 1.8, and then you're going to add 32 to that. Okay? What you'll notice is if you put the 0 in here, you would have gotten 0, and then you need to add 32, right? Get 32 freezing. So these are the body temperatures again. Your body temperature is going to vary from person to person and change throughout the day, but it's going to be a fairly limited range of just like a degree or two, okay? It's not going to be a huge difference, right? But yeah, if you're like running around, you might get up to something close to 100, okay? But if a human body temperature rises above 40 degrees Celsius, which is 104 degrees Fahrenheit, you have a condition which is called hyper greater, right? Thermia temperature. So hyperthermia. And this is going to be where you can cause convulsions, coma, and permanent brain damage, okay? And that's why if you ever get a fever greater than 104 degrees Fahrenheit, right, you go to the hospital, okay? If you can't get to the hospital, they give you aspirin and they put a cold towel on your brain, right, your head, okay? Why are they putting a cold towel on your head? What's happening is your body is trying to cook whatever is invading you, okay? Whatever the infection is. It's trying to raise the temperature so high that they can't take it, the bacteria or the virus, right? And it works most of the time to some degree. But if it gets beyond a range, your body will no longer be able to function. And so your brain, being very sensitive to that, will no longer be able to get enough energy and will start misoperating and having problems. And you'll, of course, go convulsions. You can go into a coma. And if it goes long enough, permanent brain damage. Okay, and you can actually die. People used to die all the time, actually, before we had aspirin and modern medical, from fevers. And people still do, actually, in this planet, unfortunately. So, if the body temperature drops below 35 degrees Celsius, 95 degrees Fahrenheit, you have a condition called hypothermia, That is incorrect, and I've forgotten to change it now 3 times. So, at the end of this, if somebody reminds me, I would appreciate it. So, hypothermia, hypo less, thermia temperature, right? And this is going to be where you feel cold, typically, though you don't have to feel cold. This is your body temperature is lower. It can actually sometimes present as feeling hot because your body temperature is low. Anything that touches you can end up feeling hot. You'll have an irregular heartbeat, and you'll have a slow breathing rate. Now, interestingly enough, if you're just hypothermia and you don't have it so cold it starts crystallizing the water in you, you will actually be able to survive that for a very extended period of time. People can go into hypothermia for like days and survive it. So it's actually kind of interesting. Now, having said that, does anybody know which of these is actually more dangerous to a human being? In terms of like being hot outside or cold outside? Who here thinks hot? It's hot outside, am I in a lot of danger? Okay, who thinks cold? Pretty even. Cold is by far and away the more dangerous thing to human beings. About 2 to 3 times the number of people die from cold as they do from heat in any given year. Okay? And it's kind of an interesting thing because biologically speaking, raising your temperature is more dangerous. Okay? But, we developed that way, right? So your body already knows that. You evolved to avoid that. And so you have all these mechanisms to keep your body from heating up. You don't have a lot of mechanisms to keep your body from cooling down, actually. Mostly the only thing we've done is we have a little bit of shivering and some blubber that can develop. But for the most part, we've adapted to that socially, not biologically, right? So if you don't have everything set up, house, heat, fire, you are in big trouble. This one, no, you just need enough water and you're good. Okay? And maybe get out of the sun, but that's probably because you're just not used to the sun. People can get pretty used to the sun, actually, surprisingly so. Now, energy. Energy is going to be the capacity to do work or supply heat. Stored energy is called potential energy. So you have the potential to release energy. Kinetic energy is going to be the energy of motion, so it's being used. Energy takes various forms. It'll never be created or destroyed, though, okay? It can be released from molecules. It can be released from atoms. It can be changed, modified, whatever. Never created or destroyed. That's called the law of conservation of energy. And together, conservation of energy, conservation of matter, nothing is either created nor destroyed, right? It's just changed. The SI unit for energy is the joule. This is a capital J. A calorie is actually the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Please note that you're probably thinking of food packages right now. This is a lowercase c. The food package is capital C. Okay? Like so. And so capital C calorie is actually a kilocalorie. But for some reason, they thought people were too stupid to know what a kilocalorie was and put capital C calorie. Which they're not. People use kilogram all the time, right? So I don't know what to tell you there, but I definitely would not have made that decision. That was bad decision making. But 1 capital C calorie is 1,000 small c calories. Okay. So you can raise 1 kilogram of water 1 degree Celsius. Okay. I don't know what to say there. The heat and specific heat. So heat is a type of kinetic energy. It's going to flow from a warmer body to a colder body. That heat is, again, a form of energy. Okay? It's just randomized kinetic energy. Okay? So every substance has the ability to absorb or lose heat as the temperature changes. And this ability to gain or lose heat and how quickly it does is going to be the specific heat capacity. Okay? Or shortened to the specific heat of that substance, right? So this is going to be the amount of heat that's needed to raise the temperature of 1 gram of that substance by 1 degree Celsius. So this would actually be the formula, which would be the specific heat, SH, usually shortened, is the heat, and that can be in calories or joules, typically in joules, that's going to be required, that's divided by, to raise 1 gram of the substance, 1 degree Celsius. Notice this right here, that's capital delta, okay? That means change in temperature. So you're changing the temperature 1 degree Celsius. Okay? And we don't state the ones when they're on the box, right? And so we just put grams degree change in temperature. You'll notice that metals have low specific heat values. That's why if you put a pot or pan on an oven, it heats up real fast, right? And that's why we use metal pots and pans, because we don't want to have to wait, 10 minutes for the dang pan to heat, right? We want it to heat in a minute or two. Water has a very high specific heat. Anybody know what the leading use of energy in any economy in the world is? Managing the temperature of water. Okay? Literally, usually between 50 and 70% of energy in any given economy is just used to do things like boil water, cool water, heat water, move water around. Water is important. You'd be shocked. Even if you think about the data centers, right? All that data center heat usage, a lot of that heat usage is just water management, isn't it? Purifying water, moving water. Okay, so this right here is your specific heat. What you'll notice about the specific heat is that water is the definition of that unit of specific heat, isn't it? So 1 calorie heats 1 gram of water, 1 degree Celsius, isn't it? And so that is actually the definition of a calorie, right? Is the specific heat of water, because that's where it came from. This is the human body. It's pretty close to water, and that's why it takes quite a bit to heat or cool you. You have a little bit of a buffer time whenever you're heating or cooling. Here's paraffin wax, woods. Woods have kind of a moderate specific heat, but like here's silver and gold and copper. And so that's why you see those a lot in like electronics and stuff, because they can cool really fast. Okay? They can transfer heat out really fast. Right? Right here is iron and stainless steel. Better than the organic stuff and most of the ceramics and stuff. But, not gold, silver speeds. But you don't want to think of how expensive that would be, right? Pan of gold, silver, or copper. And they'd be really soft. Wouldn't be very useful. Aluminum, kind of a moderate value. That's why if you ever use aluminum, you typically use it for like baking cookies and stuff. Because it actually has a more moderate specific heat, doesn't heat up really, really fast and get super hot. And so you don't burn the bombs of your cookies. And, you can take them out of the oven, start cooling them. And it gets that, like, nice, still kind of gooey. Everybody knows what I'm talking about. Yeah. So, states of matter. This is going to be your solids, liquids, gases. Okay. And that's going to be the physical form in which the matter exists. The three most common states are going to be, again, that solid, liquid, gas. And here we see solid water, liquid water, and gaseous water being the steam that would be coming out of this, okay? You've been seeing a lot of gaseous water coming out of tailpipes, freezing to solid water lately. You guys know that's what comes out of the back of a car, right? That white plume. Funny little side note is that if you ever look for pictures of pollution, about 80% of those pictures of so-called pollution are these white clouds above these factories or coal burning plants or something, right? Not black, brown, gray, none of that. White clouds, right? If it is a white cloud above it, that is gaseous water freezing to solid water. So they're showing you water clouds and then going pollution. Scare. Which I find so amusing. It's just like that damn plastic island pictures. Like there is a big problem in plastics in the ocean. But everybody shows this like island looking thing of plastics. It's like a solid one piece, right? And that exists in the Pacific. That's probably what you think it looks like, right? No, that is not in the Pacific Ocean. That is an island. There's actually a mountain nearby it. If you look really close, see most of those pictures, you can see the mountain. There's not a mountain in the middle of the Pacific Ocean, just floating on the ocean. That garbage patch in the Pacific Ocean, it's like half a foot below the ocean, so you can't see it from above, and you can't get a good picture. And then the garbage is like a garbage bag every 3 feet. Okay? It's not super densely packed. Huge area, don't get me wrong. A lot of garbage, a lot of plastics. It is not pictures. I mean, you actually can tell it really easy because there's always tires in the pictures, right? Do tires float nicely? No, they don't. Like, come on, kills me. States of matter. So when we're looking at states of matter, if we have a solid, this is going to be very orderly arrangement. It's going to have very tightly packed together particles. And they're only going to move very slightly, right? So when you press on the solid, it doesn't really move around much, does it? Okay? And so solids are going to have this, their big designator. They're going to have a definite shape and volume. Okay? This desk, your computing devices of whatever type you have, your notebooks, they are not changing their shape and volume all the time, right? They have this definite one. Okay. Now, definite does not mean completely unchanging. Okay? You can change their shape, right? But it takes some sort of effort. Okay. They just don't go, poof, they're everywhere. Okay. Now, if we're looking at a liquid, these are going to have particles that are going to be less orderly. They're going to move more freely. Okay. You can think of it as you broke 20% of the connections. So think of a bunch of people and they're all holding each other's hands, right? And so if everybody holds each other's hands, they can't really move anywhere, can they? Because they're all stuck, right? And that's a solid. If you were to just disconnect about 20% of those connections or so, well, groups of people can start moving around, can't they? And then they can flow and change and modify their size, right? And so you get a liquid. And so liquids have a definite volume, but it takes the shape of whatever container it's in, right? And you can play around with the liquids near you and you can see, like, definite volume, my liquid's not expanding to fill the room, right? But, if I spill this out on the desk, it's going to take the shape of the desk, right? Not going to do that. That makes a mess. All right. So, particles and gas. We're going to have no orderly arrangement. They're going to be very far apart from each other and interact very little because they're very far apart, kind of like you and the person on the other side of campus. Maybe you go, hey, but you don't do more. Going to move at very high rates of speed compared to the others. They're going to collide with each other quite often, and they'll collide with the walls of the container as well. And this is actually what you're feeling when you're feeling a solid. Does anybody have a mostly empty container that you can squeeze? Oh, try to squeeze your Gatorade for me if you would. Be so good. See how you can squeeze that in a bit? But if you squeeze it too much, it doesn't go further, does it? Yeah. And so what you're feeling there is that air headspace. Okay? And so you can change the air headspace pretty easy, but only up to a point. Once you get past that point, they're going to start banging into the sidewalls with a lot of force. And so you can't push any further. Okay? Now, the gas, this is going to have no definite shape or volume. It's going to expand to fill the container in which it's placed. And we know that from the gas around us, right? We can actually feel the gas around us. Can't see it. But it expands to take the shape of this container, which is the room, the world, etc. And it doesn't have a definite shape nor volume, does it? Like, okay, I got the gas separate catched. It expanded all the way, didn't it? This is going to be somewhat childish, but it is the best example I can give that's the most memorable. Okay? Let's say somebody were to fart in the room. Okay? We'll blame it on this person right here. Okay? The blank person that doesn't exist. All right. And so they fart in the room. They release gas, don't they? They release a hydrogen sulfide, in fact. That's what that smell is. Okay? And some methane. Now, when that fart comes out, it was only a very tiny amount of gas, right? But it's going to expand throughout the entire room, isn't it? And eventually everybody's going to smell it and go, who dealt that? Okay? And it is going to not have any definite shape. It's not like, well, it came out that way, right? It's not like it's a spear, ding, ding, ding. And only you all smell it. No, it can expand everywhere, right? It is memorable, right? And all of you instinctively knew what I was talking about. Because you've all experienced it and you all knew. All right. So this is a summary. I oftentimes will post these. I'll never mention them again. There you go, okay? If you want summary, what the heck did he just talk about? I don't remember what he talked about yesterday. These are the things. Okay, so accuracy and precision. Measuring accuracy means that you're taking measurements that are close to the actual or true value. If we were to think of a target, we're hitting around the target, but we're not necessarily hitting close to the target. We can average to get the target. So for example, if we were thinking about that target, we hit like this. Okay? I'm not that close to the target necessarily. I'm not close to each other either, am I? But if I average those values, I'm going to get the actual target value, aren't I? Okay? And so that would be very accurate, but that one's not very precise. Okay? So precision, this means that you're taking measurements. They're going to be very similar in value, but they're not close to the actual target. So this would be precise. Really, really close grouping, right? So very precise, but nowhere near the actual value. So not accurate. Okay? Very poor accuracy. Can anybody tell me what both of those would be? How would I write that to get both? I need to be very tightly grouped right on the target, right? Okay, and that would be both accurate and precise. Okay? Now, that uncertainty stuff we've been talking about, that's precision. Okay? Accuracy is actually very difficult to determine, right? Typically, what we do is we take somebody else's stuff that has done this very, very with a lot of thought, right? And worked really hard on it. We call that a literature value. And we take that as being the true value, right? And then we see how accurate, how close we were to that. Okay? But just your own measurements, getting accurate values is incredibly difficult to do. Typically, what you need to do is use a bunch of different methodologies. And we could go into that if you want. But that's beyond the scope of this course, really. Okay? But essentially, you kind of have to use a bunch of different measurement tools. Okay? So like if you were doing this with tape measures, you'd use a bunch of different brands of tape measure, ones that have very good reputation for being accurate, right? and then you'd see which one of those is, which one, what those results were, what sort of grouping you have. Okay. If you just take the measurement with the same tape measure, but it's not very accurate, like many aren't, you know how the tape measures have that little tip that moves around. It's actually meant for calibrations and stuff, but nobody does it. They just go ahead and be a quarter of an inch off. So, yeah, whatever. That's why I got a laser one. They're only like $20. Now, again, when you're taking measurements, you want to be both accurate and precise. That actually can be very, very difficult to do. Being precise is more easy for you to determine if you're precise or not. Okay? Accurate is harder, unless you know a value and what it's supposed to be. Now, these right here are the units that you would use and the dosing when we're talking about dosing. Now, healthcare professionals are going to use SI or metric units. They must also be familiar with the U.S. customary system of measurement, which is based on the imperial, though it is modified from that. And so this would be your U.S. system. This is the SI metric equivalent. That is the equivalency right there. And this is the U.S. customary equivalency right here, which is like the pounds to ounces. Be careful with ounces, by the way. There's the fluid ounce, and then there's the weight ounce. Okay? And then there's actually 2 more ounces. Also different numbers, but are not used in U.S. customary. Okay? One's British. Dang Brits. But this right here is your volumes, and so you can see things like quarts, fluid ounce right there. FLOZ is how you represent that, by the way. And this right here is the teaspoon. This is what they would convert into in terms of liters and milliliters. If you ever need to do the conversions, those are the equalities, right? Conversions would just put one above the other. Okay. Now, this is the length. This is miles and inches. It's funny that the book skipped the feet. I took this from your book. I always find that really amusing. If you're ever wondering, there are 3 meters for 10 feet. Okay? So 3.33 feet. Now, this right here is the miles to kilometers. This one right here is the inches to centimeters. And those are your equivalencies for going between SI and metric. So let's kind of talk about something more real, okay? Something you'd see in like a hospital. And so reading patient lab reports. You've all gotten your lab reports back probably from going to your physical or whatever. And let's look at that. So your patient results are going to be given along with normal values. And the result is out of the range. It's typically going to be highlighted in some sort of color, okay? Nowadays, they usually use like a green, yellow, and red. From what I've seen from Vanderbilt. Other places can use other coloring combinations. It's not like a rule. The values are going to be listed as greater than 1, but this makes the units on the numbers vary widely. Most of the units are going to be metric or some derivation of metric. Okay. Deciliter, which is DL, that's the unit volume they usually use. They usually use like you have this many units of something per deciliter. It's a very convenient unit to use for a human body because it's it's not as large of a liter. Liters, like about 2 of these is a liter. It's about half liter, and so it's like a tenth of that, right? But it's not milliliters, which you'd have a lot of milliliters in, right? And so there's actually reasons that it's used as a deciliter that are mathematical in nature and have more to do with concentrations, which we'll get into later. But deciliter, 1/10 of a liter, or 100 milliliters. Okay? And so it's a pretty, it's like a glass. Typical sort of cup unit. Right. Now, a millimole, M and then mole, is milli, 1,000th, right? And so millimole is going to be 1,000th of a mole. Okay, and we'll go into what's a mole in a bit, but we need what are atoms and what are molecules and all of that. Okay. And so a mole is going to be a unit that just counts the number of particles of something. And it's like a package of that. It's a whole lot of it. It's a big package, but it is a package of that, like saying a dozen eggs. Yeah, it's the best way for you to sort of conceptualize it. So it's like saying dozens of particles. Okay? It's a lot bigger than dozen. Now, similar units are going to be used for things like electrolytes. Those are going to be milli equivalents, which are milli again 1,000. And then equivalent is a unit that's very tightly related to moles. Okay? And I'm not going to go into the exact equivalent because you don't know like charges and stuff on atoms. So it won't make any sense. Okay? But I'm building there. Now, in the United States, your body weight is usually going to be measured in pounds. Pharmaceuticals, though, are typically dispersed in body weight in kilograms because the rest of the world uses kilograms. And many drugs are not made in the United States. So when they do dosage, did you ever notice the first thing your doctor does to you every single time? What's the first thing they do before they do anything else? Your weight. Yeah. They don't care about anything until they get your weight, right? Is that because they want to judge you? You're too skinny, you're too fat. No, they don't care about that. I mean, yeah, they're going to go, hey, you should put on some more fat if you need more fat or less fat if you need less fat. They don't really care about that. At that point, they don't care. What they're doing your body weight for is the amount of drug you need is actually directly proportional to your body weight. Okay, that's why if, say, a child takes the same amount of drug as an adult, they're going to probably have a major issue, right? Because they weigh like a third of an adult. So they need about a third of a dose. Okay? And so if you have a significant difference in body weight, for example, I was taking this drug, I was in the Philippines, and so they prescribed this drug to me. They gave me one pill, and it did nothing to me because the average Filipino person is like a quarter to a fifth of my body weight, right? And so it was like taking a little tiny sliver of a pill. I needed like 4 times the dose, right? Yeah. And so, it was bad. It did not work. Now, the calculating the dose. What you're going to do is this stepwise routine. You're going to determine the units for a final answer. This is actually the same routine as you do for any dimensional analysis. You're going to determine the given information. And you're going to determine the conversion factors to cancel your units. And then you're going to set up an equation with the given information and conversion factors. So what am I talking about when I'm talking about dosing? Well, typically this is going to be something along the lines of like 1 pill per every 100 pounds. Okay? And everybody's okay with the fact that this means per? Okay. Okay, now, if I say 1 pill per 100 pounds, if I have 1 pill and then it's written like this, one of the first things I want you to do before you start anything else, I want you to approach every problem and have this in the back of your head. You should approach every problem like this. And this is not just for chemistry, okay? This is all problems in life can be incremented towards being solved by the same approach, okay? It is how you solve problems, period, right? Whether that is a math problem, it feels unachievable in chemistry, or like an alien invasion happened and I have no supplies and I need to overcome it. Okay? Which is so achievable, it's ridiculous. So much easier in chemistry, right? All right. So every single problem can be incremented towards being solved by the same approach. You ready for it? It is profound advice. Okay. So what you do is you list, what do I have? Where do I need to go? Okay. What am I trying to get to? And then you plan out, how do you get there? Okay. And this is just a formal problem solving method. And you know, the crazy part is it sounds really like simple. Almost nobody took notes. But the success rate of people that do this versus do not do this on anything, whether it's becoming a doctor, a nurse, making $1 million, whatever, doesn't matter. Every single time they've studied this, the success rate for people that do this versus don't do this is about 3 times. This increases your chance of success for about 3 to 2.5 times. Okay. So I just gave you like super profound life advice. You're okay. I know. All right. So the first thing I want you to do whenever you do this is take anything you've been given, and I want you to put it in a form that you can actually work. Okay, 1 pill for 100 pounds. Because when you put it in a form you could actually work a math problem with, you get your brain in the math problem way, right? And so I couldn't multiply or divide this and actually do anything, right? Now I can recognize, I can multiply. Okay, so the next part I'm going to go is I need a body weight. So how many pills would somebody that is 160 pounds need of this drug? Yeah, 1.6. Very easy to do once you have it sort of set up, right? Now, formally, how would we go about that? Well, we want to cancel out pounds, don't we? Okay? And so notice I've already done the what do I have, right? I have this, that equality, right? In this case, I've set it up as a conversion factor now. I can flip that if I ever need it, okay? But I also have 160 pounds, don't I? And formally, that's what I have. Then what do I need? Well, I need to get into pills, right? And so if you're struggling, you want to formally go, I need pills. Okay, how many pills? And then how do I get there? Well, I get there by getting rid of that pounds, right? See, that has pills right there, doesn't it? But I need to get rid of pounds. So what I'm going to do is I'm going to take that 160 pounds, and that's going to be equal to, 160 divided by 100, 0.6 times 1.6, right? Notice pounds is going to cancel. I would recommend canceling your units like I'm doing right now. And then I write 1.6 pills. Now, if I gave you 1.6 pills are needed by this person, how many pounds do they weigh? Is that a different problem? No, it's the exact same problem in reverse. Okay? It's the same thing. You need the same information. There is no difference. Okay? I know I'm going to do it on the exam, and you're going to be like, Dr. Clausen, you never taught us that. And I'm going to go, how did I not teach that? And we'll have a disagreement about it. But all you would do is you have 1.6 pills, right? You want to go backwards. Do you guys know what this is, by the way? Yeah, I'm doing what's called railroad tracks usually. Everything on top is multiplication. Everything on bottom is a division. It's just a very simple way to write things out so they're organized. Okay? And it works even better on paper or on your book because you already have this line. You don't have to write that. Now, let's start with 1.6 pills. Well, I have this number here. 1 pill for every 100 pounds. I can always flip that. It's an equality, right? It's just stating 1. So I put pills on bottom, right? Because I want to get rid of pills. I want to go into pounds, 100 pounds. Pills will cancel. And that's going to leave me with my 160 pounds, right? Everybody see that really was the same problem, right? We had all the same setup. We didn't. Okay. So let's talk about drop units. Pharmaceuticals oftentimes use units in drops. Okay. Now, this is not exactly the same as drops as you probably are thinking right now. The IV delivery of medications is often going to be measured in drops per milliliter. And so that's going to be GTT per milliliter. And they'll literally drop it into the fluids that then deliver milliliters into you. Okay. The abbreviation is GTT because that's short for the Latin Gouda, okay, which is drop. So it's just Latin for drops. There's been some instruments that have started just saying drops here, which I'm actually for. This can be drop factor. This will be used to determine the drip rates when prescribed volume of medicine is required in a given time period. Drop factors are going to vary with diameter of IV tubing. And so if you just transfer a new instrumentation, you actually have to calibrate these. Okay? It's not something you can just pull a unit out from the storage and you're good to go. Right? Percents in health. You have the percent active ingredient, which you all probably have seen on your bottles. This is going to be the high potency of medicines. You're going to typically add binders to those, usually something along the lines of like sawdust, essentially, or cellulose powders. This is going to increase the size of the pill. It's going to increase the amount you get to weigh out. So instead of trying to weigh out like 10 atoms, you can weigh out like 0.1 grams. Okay? So you can then actually accurately weigh it. The percent of an adult dose would be for a child. Okay? And so you would need to give a child lower dose because they weigh less. And so you'll get a percent of the dose that an adult would need, depending on their weight ratio to an adult. Okay. The percent in nutritional labeling, it's kind of a BS value, honestly, but it's a guideline that's kind of helpful if you know what you're doing with it. The nutritional labels list the amount of carbohydrates, protein, and fat, as well as the percent daily value. That's the percent DV. And it can show the contribution of the single serving to a suggested daily dietary requirement, and we'll leave it off on there. Okay. You can come in next time with this having bothered you the entire time and know the answer. Okay. Okay. You all have a wonderful day. I'll see you all next time. And I'm going kind of slow, aren't I?
Thank you.
Okay. Thank you. You have a wonderful